Hello and welcome to Organic Chemistry 1. In this video, we're going to work on reviewing some of our skills in drawing Lewis structures from general chemistry. The ability to draw Lewis structures quickly and correctly is a core skill which is central for success in many other parts of the course. The idea of a Lewis structure comes from structural theory. Structural theory is a framework within chemistry that states that a chemical substance is defined by a specific arrangement of atoms within that substance. Furthermore, that these atoms within a substance tend to have predictable arrangements, and that stable molecules tend to have atoms arranged in a way that maximizes filled octets. You've learned about this in general chemistry as an example of the octet rule. In organic chemistry, we'll take it one step farther and we'll see that the structure of a molecule determines the properties of that molecule. If we know which atoms are in that molecule and how they're arranged, we can make predictions not only to the physical properties of the molecule, but also to the chemical behavior of the molecule. For example, let's take drawing a Lewis structure of a simple molecule. Now, I want to start out with a disclaimer that I'm going to go through the process of drawing a Lewis structure the way we teach it here at UNC Charlotte in our general chemistry courses. You may have learned a different process with some different steps of how to draw a Lewis structure. Any method of drawing a Lewis structure is fine, so long as the structure at the end of the process is legal and possibly correct. Let's start with a molecule with a molecular formula of C3H8O. If we're drawing a Lewis structure for this molecule given no additional information, we would want to first start by counting the number of electrons in the molecule. If you don't remember how to do this, I would highly recommend looking up valence electron counting in your general chemistry textbook. For this molecule, with 3 carbons at 4 valence electrons apiece, 8 hydrogens at 1 valence electron apiece, and 1 oxygen at 6 valence electrons, we would come up with a total count of 26 electrons. The next step in the process would be to build a simple skeleton. Now, when we're building this skeleton, we want to keep a few things in mind. First, that hydrogen and halogen atoms are usually terminal. Typically, they're only connected to one other atom, so we never want to start building a structure with one of those atoms unless we have a very good reason to do so. All other atoms are going to be considered to be internal. They're going to build the skeleton onto which we will hang all of those terminal atoms. And if we have to make a choice, we're going to tend to choose the least electronegative atom as the atom to build from, since less electronegative atoms frequently are able to form more bonds than more electronegative atoms. So in the case of this molecule, we would start by connecting some carbons together. Here I've taken my 3 carbons and I've connected them in a line. I have no other reason to think that they may not be connected this way, so this is a fine place to start. After that, I want to move on to my next internal atom. Now, below the molecule, what I'm going to do is I'm going to keep track of all of the atoms that I've added so far. So right now, this postulated molecule has a molecular formula of C3H0O0. I'm also going to keep track of all the electrons that I've used so far. By connecting these 3 carbon atoms together, I have made 2 bonds. Each bond contains 2 electrons, so right now we're at an electron count of 4 out of our 26 electrons. Next, I want to move on to the other internal atom, which is the oxygen. Since I have no reason to put it anywhere in particular, I'm going to add it to the end of the chain. Note that I could have added it to the middle of the chain, which would also be a potential valid structure. I've just chosen not to do that. A molecular formula will rarely give us a single unambiguous molecular structure that we can draw. Since I've added another bond, we're now up to 6 out of 26 electrons. Now that I've exhausted my internal atoms, I'm going to move on to my terminal atoms. I'm going to add hydrogens to this structure, and I'm going to be very careful to maintain the octet rule while I do so. So I'm going to add 1, 2, 3 hydrogens to the carbon on the left. This will satisfy carbon's octet, meaning I should move on to the next atom. That carbon can accommodate 2 hydrogens. Now it has a filled octet. I'll move on to the next carbon, which can also accommodate 2 hydrogens. Then my last hydrogen needs to go on the oxygen. So here, my molecular formula is now matching the molecular formula of my question, C3H8O, but I have only used 22 out of 26 of my electrons. So my next step is to add my remaining electrons as lone pairs. A pair of electrons is going to go onto an atom in the molecule. In this case, the way I choose which atom gets those electrons is fairly easy, since my oxygen atom has only 4 out of a possible 8 electrons. So my lone pairs are placed on the oxygen, now giving me a molecular formula of C3H8O with 26 electrons. So this is a potentially valid Lewis structure given that formula. Now sometimes we would need to make multiple bonds to fill octets by shuffling electrons around the molecule. We'll see an example of that later. What about ionic molecules? The molecule that we just drew is a neutral molecule with no formal charges, but what happens if we need a molecule that does have charge on some atoms? For this example, I'm going to say let's draw a Lewis structure for CaCO3, or calcium carbonate. Now, the first question we need to ask is, by looking at that formula, how do I know that this is an ionic molecule? Well, it's because we have an atom in groups 1 or 2 combined with atoms in group 5, 6, or 7. In the case of this molecule, we have the calcium atom from group 2, and we have some oxygen atoms from group 6. Those two together mean that this is going to be an ionic molecule. So when we're drawing this, we're really drawing two separate fragments, a calcium 2+ ion and CO3 2-, another polyatomic ion. In this case, this one has a name. This is the carbonate anion. Now, it would be a good idea here to review the ionic charges of different atoms, as some atoms, like calcium, only ever exist in a single charge state. So we're never going to see a calcium +1 or a calcium +3. With that in mind, let's go ahead and build the structure. So my carbonate ion here is going to have all the valence electrons from this molecule. We have a total count of 24. So the calcium ion is easy. We can just draw Ca2+. Then, going through our process, we would take the carbonate ion and we would start building a structure, starting with the least electronegative atom, the carbon. And onto that carbon, we're going to build a framework with the other internal oxygen atoms. Now, note here that I could have put all these in a line, but I didn't because I have a particular molecule in mind. Now, when I ask you to draw a Lewis structure in class, I'm going to grade your Lewis structure based on whether or not it's plausible, not based on whether or not it's exactly the one I was thinking about. As the course progresses, we'll need to get better in knowing which structures are plausible and not plausible, but for now, any legal Lewis structure is correct. All right, at this point, we've used 6 of our 24 electrons. We have all of our atoms, which means now we need to add lone pairs. So I'm going to go around and I'm going to start adding lone pairs to these atoms to satisfy their octets. So the first 3 lone pairs are going to go on oxygen. That satisfies oxygen's octet and gives me 12 out of 24 electrons. Now, why did I start on oxygen and not on carbon? Generally speaking, when we're adding lone pairs to atoms, we want to pay attention to the electronegativity of each of the atoms in the molecule. So in this case, I've started with one of the oxygen atoms, since oxygen is more electronegative. That means the next 3 lone pairs will also go on oxygen. The next 3 lone pairs will also go on oxygen, and that gives me 24 out of 24 electrons. If we examine this structure, though, we know we're not done yet, because carbon lacks an octet. So what we need to do now is we need to move a lone pair of electrons to fill the octet of that carbon if possible. Organic chemists use a particular shorthand in order to indicate the movement of electrons within a molecule or between molecules, which is a curved arrow like this. So what this arrow says in words is take this lone pair from oxygen and share it with the adjacent carbon. In doing so, we've now created a double bond between carbon and oxygen, and we can see that all the atoms in this molecule now fill their octets. We're not done yet, though, because this molecule is a polyatomic ion, meaning we have to add some formal charges to atoms. Again, you may have learned a different method for how to calculate formal charge, but I'm using this one because I like it the most. The simplest way to calculate formal charge for an atom is to look at the group number of that atom and subtract the combined number of bonds and dots. Remember that formal charge is a way of sort of bookkeeping, to say which of the atoms in the molecule is responsible for the charges that we're actually observing. So here the group number of the atom tells us how many electrons the neutral atom should have, and each bond and each dot indicates a single electron that that atom owns. If we take the difference of those two, that'll tell us if we have too many electrons, meaning a negative charge, or too few electrons, meaning a positive charge. For example, if we look at calcium, the calcium atom is in group 2, and so we subtract 0 bonds and 0 dots, ending up with a sum of +2, or a 2+ formal charge. Looking at the carbonate ion, we can start with this oxygen on the left. Oxygen is in group 6. We see 1 bond and 6 dots. That would be 6 - 7, meaning that atom should have a -1 formal charge. Now this is going to be true for the oxygen atom on the right. The nice part about doing it this way is that all atoms with the same bonding patterns will always have the same formal charges. How about the other oxygen and the other carbon? Well, those two atoms have 0 formal charge. Don't just take my word for it, though. Take a moment here and pause the video, do the calculation, and see if you can convince yourself. So what about the other two atoms? Well, the carbon and the other oxygen both have 0 formal charge. They are formally neutral. Don't just take my word for it. What I'd like you to do here is pause the video for a moment and work through this calculation and see if you can't convince yourself that I'm right that both of these atoms should have 0 formal charge. All right, so let's check our work here. The carbon atom is in group 4. It has 4 bonds and 0 dots. That would indicate a 0 formal charge. The oxygen atom has a group number of 6. It has 2 bonds and 4 dots. It also has a 0 formal charge. So that means that we verified everything about this structure and that this is a plausible structure for calcium carbonate. So where do we need to go with this? What we need to be able to do is we need to be able to draw Lewis structures for fairly complex molecules, and we need to do it quickly. So other skills we'll need to work on are how do we draw a Lewis structure for a molecule with many more atoms like C5H11NO? Are there double bonds in this molecule? Is there a ring of atoms? Is there some way to tell from looking at the molecular formula? Are there formal charges? Where do they go? And then we'll need to extend this farther into talking about things like molecular geometry. So what shape is this molecule? What does it look like in three-dimensional space? We'll build onto this. So what sort of intermolecular forces will the molecule that we draw experience? How will this thing react? It's all based on being able to draw a Lewis structure for these molecules, so make sure you practice this skill.